Hey, before we continue, please consider subscribing to two excellent channels about IT, Avocodus and AveTech. Avocodus is a great channel with programming tutorials and IT humor, and AveTech is about the stories behind tech and business. Links are in the description. Thank you.
So today I'm going to talk about Poisson regression models for count data. I will first of all give a brief review of regression analysis. I will then introduce Poisson regression and looking at a simple model without a covariate, first of all, the so-called equiprobable model. I will be then assessing this particular model with the Pearson chi-square test and the log likelihood ratio test statistics, and also I will be looking at some residual analysis as well. And then I will be introducing the Poisson regression model with a covariate, so basically a Poisson time trend model. You may have come across different types of regression models already. For example, a linear regression model for a continuous dependent variable. You may have used logistic regression models already for a binary outcome variable. There are obviously other types of regression as well that are also part of the generalized linear models. So basically, for example, the multinomial logit model for a multi-category unordered variable, and also the sort of so-called cumulative logit for multi-category ordered variables or ordinal regression. Here we are going to basically go a step further. We are going to look at the outcome variable that is a count variable using Poisson regression. And sometimes in the literature you may also find the expression of a log linear model. Data for this particular session are assumed to be, first of all, a count variable y. So for example, the number of accidents or the number of suicides in a particular geographical area or time period. Then we've got a categorical variable x, for example, with, let's say, capital C possible categories such as days of the week or months. So basically y here in this particular case has capital C possible outcomes, so y1, y2 and so on until yc. Obviously, generally in Poisson regression modeling you may think of a number of categorical variables that you have, or a number of even continuous variables as explanatory variables in your models. Here we're going to start with something relatively simple. Just to sort of introduce the basic principles of Poisson regression. So basically it's a form of regression analysis here to model count data, and a particular case, if all the explanatory variables are categorical, then we basically model a contingency table, so basically cell counts. And the model basically models expected frequencies. The model specifies also how the count variable obviously relates to any of these explanatory variables, or for example of the level of the categorical variables. Poisson models is a form of generalized linear modeling. It uses the logarithm, the log, as the canonical link function in this particular case. We basically assume that the outcome variable y, the dependent variable, the variable that we are particularly interested in, has a Poisson distribution, and the logarithm basically is its expected value that can be modeled by a linear combination of any of these unknown parameters. So basically of these unknown beta coefficients, the regression coefficients in your model. Sometimes it's referred to as a log linear model, in particular when used to model contingency tables. Let's have a look at a brief example. For example, the number of suicides by weekday in France. So we've got a number of weekdays in the first column, and in the second column just simply the frequencies, the occurrences, the events, and then let's say the percentages, how it is distributed according to days of the week. So that is the type of model or type of data that we would like to model. Let's first look at a very simple case, the equiprobable model. The equiprobable model means that basically all outcomes are equally probable, so they're equally likely. That is, for our particular example, we assume a uniform distribution for the outcome across days of week, so y does not vary with the days of week x, basically. So the equiprobable model is basically given by this formula here. So the probability of a particular event across these categories, basically of the days of the week, is equally distributed. So it's 1 over c, so 1 over the capital C. So we basically expect an equal distribution across days of week. And given this particular data, we can test then the assumption of our interest, basically the assumption of the equiprobable model, so H naught, that this assumption holds. So looking at our example again, let's say suicides by weekday in France, basically H naught, the assumption that we would like to test, means that each day is equally likely for the suicides to happen. That means the expected proportion of suicides is about 100 over 7, so 7 days of the week. So basically just over 14% per day. And if you're looking at the third column of the table, we see the actual observed distribution, and obviously that depends a little bit on each day of the week possibly, and diverges a little bit from 14% per day. But maybe the divergence is not very much, and we are satisfied with actually our assumption. And to do that properly, you obviously would need to do a formal test, and I'll come to that in the next session, and I will explain the actual formal test in further detail. Looking at another example, example 2, looking at traffic accidents per weekday. Again, we want to make the H naught assumption of the equiprobable model. That means that each day is equally likely for an accident. That means the expected proportion is again the number of accidents is 100 over 7, so basically just over 14% per day we would expect. And there, maybe in this particular example, we see a greater distribution. In particular for Sundays, there seems to be a greater percentage than just 14%. So we may want to continue testing if the observed distribution that we have is maybe different from the expected distribution, or if it's still okay to assume that they are actually equal. Looking at hypothesis testing, we may say in this particular case H naught that each day is equally likely for an accident to happen, but we can also think of other alternative null hypotheses. For example, that each working day is equally likely for an accident, or that maybe Saturday, Sunday, the weekends, are equally likely for an accident. You could also think, of course, of other extra or additional variables. For example, the distance driven each day of the week, and you may want to take into account those types of explanatory variables as well. Just thinking about this a bit further, basically we can now express the equiprobable model more formally as an actual Poisson regression model without a covariate, and that models the expected frequencies. So basically we assume a Poisson distribution with parameter mu for a random component. That means the response variable y follows a Poisson distribution. That means basically that y follows this notation here, or this formula here, using the exponential function, and mu the parameter of interest, and also the y the outcome variable of interest, where y is just simply the count variable 1, 2 and 3 and so on. So basically y is a random variable that takes on only positive integer values, and also this Poisson distribution has only one single parameter mu, which actually is the mean and the variance of this distribution. And we assume that our outcome follows, this Poisson distribution follows the integer count distribution. Looking at basically the simple models to start with, we aim to model the expected value of y, and it can be shown that this is the parameter mu, hence we aim to model the parameter mu effectively in our Poisson model. So defining the equiprobable model that I had on an earlier slide, sort of the intuitive notation, I'm now formalizing this, writing it down as the expected value of y, mu, basically the parameter mu, and that is then 1 over c, because we are making the assumption of the equal probability across weekdays. Or using the link function, the log of mu would then be a coefficient alpha. So that is basically the coefficient that I would like to estimate as part of my model, and alpha is then basically the log of 1 over c in this particular case. I will now continue looking at a goodness of fit test statistic for Poisson regression. So we would like to test if a particular model that we are assuming really does fit the data, or if you may want to extend our model and include maybe more covariates in our model. We first of all look at another example. So I will first of all talk that through, and then I will be discussing goodness of fit test statistics, so the Pearson chi-square test and the log likelihood ratio test. So we've got the example of recall of stressful events, so example 3. And basically we would like to first of all start with something simple again, a simple Poisson model without any covariates, but then extend this to an example with covariates. So basically participants from a randomized study were asked if they can recall any stressful events over the last, in fact, 18 months. And if yes, in which months? When did this particular stressful event happen? And we then wanted to look at the number of stressful events that people were able to recall and look at their distribution according to these 18 months. So we had 147 stressful events recorded in total. So the H-naught hypothesis is that first of all we start with something very simple, start with some very sort of conservative attitude, conservative assumption that these events are uniformly distributed over time. That basically means that H-naught follows the equiprobable model, that all these probabilities across months are the same. So we have an event occurrence of 1 over 18, so a particular event can occur in any given month. So that would be a percentage of 0.055, or in terms of percentage terms, it's 5.5%. So we would expect about just over 5% of all events to happen per month. Looking at the actual count data, that was recorded. So we've got first of all months ranging from 1 to 18. And then we've got the actual count data, so the actual number of events that were recorded per month. And then the percentage that relates to the actual count variable. So we can already see that some counts are significantly or are actually higher than 5.5%, and some are actually a bit lower than 5.5%. So just looking at the data, we may already conclude that there is some divergence between, or discrepancy between, the observed values and what we would expect to see based on our equiprobable model. Let's look at the evaluation of the Poisson model, doing this more formally. So we would be using the Pearson chi-square test and the deviance, or also called the log likelihood ratio test for Poisson regression. Basically both are goodness of fit test statistics, and they basically compare two models. One for the current model, the model that we have at hand, so in this particular case the equiprobable model, and then we compare this model with this so-called saturated model, i.e. the model that is larger, that is the saturated model, that is the model that fits the data perfectly and that explains all of the variability. That basically means we are comparing observed and expected frequencies. Looking at the Pearson and the log likelihood ratio test statistics, basically we say that if H-naught is true, that means that if the equiprobable model actually holds, then we would expect overall the a distribution of 147 times 1 over 18, so that we would expect an expected frequency of just over 8 per month basically. So we basically have one parameter model that we would like to estimate, and that would be just over 8 events per month. So we can compare the count or the observed counts with the expected count per month, and we can see that obviously some counts are quite a bit higher than maybe 8, and some counts per month are quite a bit lower than 8, than what we would expect. Looking at the Pearson chi-square test, it allows us basically to compare the observed and the expected frequencies. and you may have come across the Pearson chi-square test when testing associations between two categorical variables. So it's the same principle effectively here. We are trying to compare observed and expected frequencies, and basically it allows us to look at the sum of the standardized residuals in squared terms. And we can calculate this particular statistics for our example. So basically you just have to plug in the numbers for each cell basically. So we've got 18 cells in total, and for this particular example, recall of stressful events, we will have the chi-square test statistic of 45.4, and we now need to compare this to the value from a chi-square distribution. So basically the assumption is that if H naught is true, if indeed the equiprobable model holds, then this test statistic will follow the chi-square distribution. So we can compare it with the distribution from the chi-square tables, for example. So for that we need to have the degrees of freedom, which is defined as the number of cells minus the number of model parameters, which is the number of cells is 18, so capital C, minus the model parameters here. In this particular case for the simple model is just 1, because we have got only alpha that we need to estimate. So we've got the chi-square test statistic of 45.4 with basically 17 degrees of freedom, so 18 minus 1. At the 5% significance level, looking at the chi-square table value, we've got 27.6 from the table. And also we have got that basically associates with a p-value of really rather small, 0.001. So that means the value we would then reject H naught based on those characteristics. Conclusion is that there's strong evidence that the equiprobable model does not fit the data. So just looking at the actual data from our table, we already looked at observed and expected frequencies, and we already saw some discrepancy, but exactly how significant the discrepancy is, the discrepancy between observed and expected values, we can then formally test this, for example here with the Pearson chi-square test, and we concluded that the difference is rather large, so it's not just due to chance, and that the data does not follow the equiprobable model. So we have to do probably something else to improve this particular model. Likewise, looking at the log likelihood ratio test statistics for Poisson regression, we can now also use this test statistics to again compare observed and expected frequencies. So basically the formula here gives the log likelihood ratio test statistic, and you can plug in the numbers, the observed and the expected frequencies, and that is again a measure of the fit of the model, so the goodness of fit test statistics. And again, similarly to before, if H naught is true, then actually this particular log likelihood test statistics would follow a chi-square distribution. So again, we need to define the degrees of freedom, which again is the number of cells minus the number of model parameters. So again, it's 17 for our example. And the log likelihood ratio test statistics for our example is 50.8 if you plug in the numbers on 17 degrees of freedom. So we've got a p-value of less than 0.001 again, and we would again reject H naught. So basically in the same way as with the Pearson chi-square test. So the conclusion is again the same. There is strong evidence that the equiprobable model does not fit the data. So we basically now need to use this information to take this forward and to think about possibly fitting a more sophisticated model, maybe including another covariate to allow for differences between number of months. Just a couple of remarks about the Pearson chi-square test and the log likelihood ratio test. They're basically asymptotically equivalent. So basically they're relying on a large sample, and you would expect them to be giving you basically the same or very similar results. If they're not similar, this could just simply be an indication that the large sample approximation doesn't actually hold. And also, just to note that for fixed degrees of freedom, so when n increases, so for larger samples, that the distribution of the Pearson chi-square test usually converges to the actual chi-square distribution, and also it does it more quickly than the log likelihood ratio test. And also to note that the chi-squared approximation is usually relatively poor or not appropriate if any of the expected cells are less than 5. Let's look at some diagnostics as well in Poisson regression models. So I will introduce some residual analysis briefly, just to sort of introduce some of these ideas as well, although we've already discovered that based on the log likelihood test statistic and the Poisson chi-square test statistic, the model may not hold, but let's look at what it does to the residuals and introduce what type of residuals there might be for Poisson regression models, and then we can later on extend our model to a more sophisticated model, in particular using a categorical variable in the model, or using another explanatory variable in the model. So let's look at diagnostics in Poisson regression models, residual analysis, and let's continue with our example from our previous session about the recall of stressful events. Residuals represent variation in the data that cannot be otherwise explained by the model, so that's quite a nice feature generally about residuals, and they can help us. Residual plots can help us to understand our model better and to diagnose any particular problems. So the residual plots can be used to discover certain patterns, certain outliers, misspecifications of the models. So basically, ideally, we would like to see a sort of random pattern in our residual plots. And if there are some sort of more systematic patterns, then we can identify certain particular problems, and it can help us to reformulate the actual model. So if the residuals exhibit no pattern, then in a way that's a good indication, because that would imply that the model is probably appropriate for the particular data at hand. I would like to introduce three different types of residuals for Poisson regression models. So the raw residuals would just be the difference between the observed and the expected values. The Poisson residuals or the standardized residuals are basically the raw residuals divided by the square root of the expected values. And then also the adjusted residuals, and they can be rather helpful for actually the diagnostics and the actual plots that we are going to look at. So that is defined as the observed minus the expected values divided by the standard deviation of these observed minus expected values. So basically we've got adjusted residuals that we would like to look at and to use for our residual plots. So if H0 is true, the adjusted residuals have a standard normal distribution with a zero mean and a standard variance of 1. So basically, at least for large samples, that should be the case. And looking at that for the recall of stressful events example, that basically means that we look at the adjusted residuals, and we would like to see how they compare. So we compare the observed and the expected values divided by the standard deviation of that. So we obtain the adjusted residuals, and for each category, basically for each month, we look at the adjusted residuals that are greater or smaller than 1.96, comparing it with the normal distribution that would hold if H0 actually holds. And if you see this bigger discrepancy, so adjusted residuals larger than 1.96 or smaller than minus 1.96, that would give us an indication that there is divergence from the H0 hypothesis. So if the adjusted residuals follow indeed the normal distribution, which is true under H0, we would expect roughly one adjusted residual being larger than 1.96 or smaller than minus 1.96. So we would only be finding one large or very small adjusted residual we would expect. Now looking at the actual data, we saw that in months 1, 3 and 4 we had actually positive adjusted residuals, and in months 16 and 17 we had negative adjusted residuals that are larger or smaller than 1.96. And basically we see that it's actually more likely to report more recent events. So the positive residuals means that observed data is larger than the expected data, and it's more likely to report a stressful event in the months immediately prior to interview. So we do see some sort of time trend probably in our data set that obviously isn't captured with the equiprobable model. So we want to define our model in a better way or improve our model, and we see in the next session how we are going to do that. looking at the plot of adjusted residuals per month, we also see a downward trend. So the adjusted residuals are on the y-axis and the months are given on the x-axis, and we can see just by plotting those types of adjusted residuals that there is a downward trend. So again, it's not a random pattern, there's a downward trend, and we might see basically the sort of time trend. Another way of looking at residuals are the normal QQ plots. So basically these are probability plots that plot the quantile of one distribution with the quantiles of another distribution. And here we would like to compare the distribution of the observed adjusted residuals with the expected residuals, i.e. the normal residuals from a normal distribution. So basically here, and Q stands for quantiles, i.e. for a quantile against quantile plots effectively. So basically we are plotting observed quantiles against these expected quantiles, and hence we have plot quantiles of adjusted residuals against the quantiles of the standard normal. That means that the points should actually lie just on the straight line of the y equal x line. At least if the adjusted residuals indeed follow the normal distribution, which is true under the H-0 hypothesis. So again, we can compare divergence from the H-0 hypothesis. And here, looking at the QQ plots from this particular data set, we can see that in the tails, so in the upper end and in the lower end, there is divergence from the straight line relationship. So again, we would conclude that there is some kind of time trend in our data set. So conclusions are clearly that there is divergence in the tails from these straight lines. There is overall strong evidence that the equiprobable model doesn't really hold, doesn't fit the data that well, which maybe isn't too surprising. And we would like to, or we'll see sort of more likely, or we see that the data is more likely to report recent events. So basically such a tendency would result if respondents were more likely to remember recent events than distant events. So basically, again, there is strong evidence that we should be using some kind of other model and which one to use. And we are going to now explore the Poisson time trend model, a Poisson model with a covariate.
Please consider subscribing to two excellent channels about IT, Avocodus and AveTech. Avocodus is a great channel with programming tutorials and IT humor, and AveTech is about the stories behind tech and business. Links are in the description. Thank you.